Hello, ladies and gentlemen, and welcome back to question number 9. It's a two-part question, and like all question 9s and 10s on the Euclid, it's purely written. Okay? So hopefully you've had a chance to click the link in the description, download a copy of the contest for yourself, and try question 9. Let's just jump right on in. Okay, so what does question 9 say? Well, 9a, in triangle ABC, whoa, that is a busy triangle. ABC is 90 degrees. We got that shown. We have some rectangles, so I'm betting there'll be some more 90 degrees in here. We have rectangle DEFG, and it's just inscribed as shown. And then we have squares JKGH and MLFN, and they're inscribed in AGD and CFE respectively. Okay, so there are these. I mean, this one JHGK doesn't really look like a square, but nonetheless, we'll assume it is. If the side length of JHGK is V, and the side length of MLFN is W, and DG, so the longer looking side of our rectangle is U, prove that U is equal to V plus W. Okay. That sounds involved. Let's draw ourselves our picture, label everything in, and yeah, and then we'll see where we can go from there. Okay, ABC, and then we have rectangle DEFG, and then we have a square in here, GHJK, we have another one in here, FN, and then I think it was M and L here. Okay. So let's just double check that we have that all right. Looks like it. Okay, so they told us that there's a 90-degree angle here, and you know what? I'm just going to add them all in here. There are 90 degrees just about everywhere else, because we have a bunch of squares and rectangles. So I'm adding these in because they bothered to tell me that this was a right-angle triangle, so I have to suspect right-angle triangles might come into this. And already we can see there are some smaller right-angle triangles. One might even suspect that they're all similar, and maybe that'll help. Now, we've got a lot of black going on here, so I'm going to label things in, label our lengths right now in blue. So we know the big length is supposed to be U. So there's a U, and there's a U. And then V goes with the JHGK, and W is MLFN. Okay. And they're squares, so all of them are that length. So we'll get some V's here. And some W's. Okay. So, what have we got here? Well, I noticed pretty quickly, remember I want to show that U is V plus W. And I notice I have a length of V here, which means that this length here, DH, has to be W. So if I could just show that, I'd be all set. Same thing over here. NF is a length of W, and EF is U. So if I could just show that EN was V, I'd be all set. Well, look at these right-angle triangles. ENM and JHD. I need a V here. I've got a V here. I need a W here, I've got a W here. So I definitely think right angle triangles are the way to go. And I'm betting there's some similarities. So what we're going to do is we're going to give a name to this angle right here. I'm going to call it dot. And so this here is 90 minus dot. And if that's 90 minus dot and that's 90, if we add them up together, we have 180 minus dot. And they form a straight line, so that means this has got to be dot. 90 minus dot, dot, 90 minus dot, dot, 90 minus dot, dot, 90 minus dot. You could use theta or really anything else. But look at all the similar triangles we've got, and they're all similar to the big one, ABC. Okay. So what can we do with this information? Well, first let's just make a note of all the similar triangles that we've got. Some of these might be congruent. For example, if I can show that DJ and EM are the same length, then that means that this triangle and this triangle have to be congruent, and so I will get my V's and my W's where I need them to be. Okay, so we'll make a big list. So, of course, the big triangle, ABC, and it's similar to, well, let's go down the list. So, similar to AKJ, it's similar to JHD, similar to DBE, similar to ENM, similar to MLC, but that's actually not all. We have a bigger triangle in here, AGD, and it's also right angle, and it's got the 90 and the dot. So we can also say similar to AGD, and we have another one over here, similar to EFC. Okay. And I think that's it for all of the similar triangles. But well, we have a lot to work with here, actually. So these last two, they have some of their side lengths being U. These two have some of their side lengths involving a W. And these two have some of their side lengths involving the V. This one here doesn't really seem to be helping, DBE, the one at the very top. I don't have a use for him right now, but all these other ones have W's and U's and V's in various places. So I'm wondering if we can get some ratios going on here. So key points of interest, which we'll put in purple, this length right here is U minus W. And this length right here is U minus V. So I'm probably going to want to use GHD and E and M. But I'm a little skeptical as to whether or not I can show DJ is equal to EM. And my reasoning for that is I'd have to start putting in other lengths. And right now I don't think I want to put in other lengths and start doing pluses and minus calculations. I may have to, but I'd like to shy away from that right now. Because we have an abundance of similar triangles, I want to use the similarity of the triangles as much as I can right now. So, what can we do here? Well, just using those two labeled triangles, so this one right here, GHD, and ENM, we can see that V over U minus V is the same, because it's a ratio of side lengths, is the same as U minus W over W. And that's since GHD is similar to NNM. Okay? So does this get me anything? Well, if I cross multiply, I'll get W times V, and I'll get U minus W, U minus V, and if I expand that out, I'll get U squared minus V plus W, ooh, that's important, times U plus VW, and these two guys are going to cancel out. There, I haven't used that one. I think that's actually it. We didn't need all the other. There's a whole bunch of similar triangles, so maybe there's a bunch of ways to do this, but... So if we rearrange, we'll get U squared is equal to V plus W times U. And since U is a length, then we know that U will not be 0. So if we divide by U, then we get, well, U squared divided by U is just U. And if we divide by U on this side, we're just left with V plus W. And that's exactly what we wanted. So not actually a very bad question A. The triangle itself was a little overwhelming because it had a lot going on there. But an abundance of similar triangles, and of course we had to make sure that we listed them out and explained our reasoning as to why they were all similar triangles. But then at that point we get a very quick ratio. And that ratio was really all we needed. So there's probably other ways you could have done this. But I avoided having to label other side lengths. I avoided having to have any pluses or minuses of the side lengths, really. So I'd say overall that was probably the cleanest way to do this question. Okay. But that was just A part. We're still left with a B part. Oh, hello. Close that. All right, B part. 3 thin metal rods of length 9, 12, and 15. Already I'm thinking that's a Pythagorean triple. But let's finish the sentence off. Are welded together to form a right-angled triangle. Okay. Which is held in a horizontal position. A solid sphere of radius 5 rests in the triangle so that it is tangent to each of the 3 sides. Okay. So what have we got going on so far? So we sort of have a little right-angled triangle, and we have a sphere, but it's not a sphere, but it's sort of resting inside. It's just touching the side. So part of it's hanging below, part of it's above. That's what we've got going on. That's the idea. So it's always a good idea to, especially with a 3D question like this, to have a mental picture. So thin triangle, sphere resting inside. Okay, and that's just with props that I have lying around. Fingers and a water droplet stress ball. Okay, so we have a mental image of what's going on. 9, 12, 15, right angle triangle, a solid sphere of radius 5. Let's continue on. Assuming that the thickness of the rods can be neglected, as is often a math assumption, how high above the plane of the triangle is the top sphere? Okay, so we have a mental picture in our mind just with our fingers and our stress ball, but let's actually draw a picture in our notebook, and we'll see what we can get to the bottom of. So I hear the words tangent to the 3 sides, so I'm thinking circles, and I'm thinking right angle triangles where radii meet. But let's just draw a picture here. So we have our right angle triangle, and it's resting in the plane. And then we have a sphere. That's a terrible sphere. Let's draw our sphere first. I want a good picture to go with. Oh, that's very nearly a good sphere. Okay, so we've got... This is what's going on right now. So we have our sphere, and it's sort of resting in here, and it's touching each of the sides. Maybe it touches here, maybe it touches back here, and it touches here. So we have our sphere, and it's tangent to each of our right angle triangles. And it's just sitting in here, and we sort of want this height. That's what we're looking at. If we were to look at it dead on, we'd sort of just have a line representing our triangle, and we'd just want this height here. But here's a more 3D projection here, and this is looking at it just from the side. Now, if we were to just look at it above, we'd have our right angle triangle. The good thing with these 3D questions is to get some perspective. So we'd have a very fat, bulbous sphere here. But when it's resting inside the triangle, it's going to hit these tangent points. And a sphere, one of the ways I like to think of a sphere is it's just a bunch of circles all stacked very tightly on top of one another. So where it hits the triangle, where it hits the plane of the triangle, it's just sort of like slicing a sphere. And when you slice a sphere, you get a circle exposed. So there's really a circle sitting in this right angle triangle. Okay? And it's going to be right below, it's going to be directly below the center of our sphere. And our sphere has a radius of 5. And if we could figure out the radius of this small circle, then we'd know we'd use Pythagoras to get this height, and then this is going to be a 5. So it'll be 5 plus this height. So we've got sort of a mental plan of attack, but we need to write it up, and we need to actually do some work. So the plane of the triangle we have a circle inside the triangle, which is tangent to each side. This is also what's called an incircle. And there is a formula for the radius of this incircle, but if you don't remember it, and I'll be honest, right now off the top of my head, I don't remember it, because I don't do many geometry questions in my day-to-day life. If you don't remember it, it's okay. They've given you a very simple case. It's a right angle triangle. And if it's a right angle triangle, we get some pretty awesome stuff. So anytime I see a circle and there's some tangents, I always connect the radius of that circle up to those tangent points. And I always get right angle triangles. Okay. So, when we do this, if we label our radius r, we notice some things. Well, I've got 3 right angles here and a quadrilateral. It's going to have to be a square, so we get some more r's here. And this side is going to be our 12, so this is 12 minus r, and this is 9 minus r. Now, one of the nice things, if you connect the, if you have 2 lines and they both become tangent to the circle, then from the point to the point of tangency, it's always the same length. This is a circle law, and it is something that I recommend you be aware of. Usually if you're attempting the questions 8, 9, and 10, you're aware of things like circle geometry. But then that tells us we have 9 minus r here and 12 minus r here. But altogether it should be 15. So let r be the radius of the circle. Then we've shown our work. 15 is 9 minus r plus 12 minus r. That's 21 minus 2r. So 2r is going to be 21 minus 15, that's 6. R is going to be equal to 3. All right. And 3 is a pretty good number, because we had another one that's 5, and both of them are going to become a right angle triangle. So that should solve the question pretty quickly. So our big triangle, or big sphere, has a radius of 5, so we can put some 5s in here. And now we have a 3 here. So the top of the sphere is 5 plus h above the plane. We don't really care about this part of the sphere that's hanging down. So 5 plus h, it remains just to figure out what h is. But now we have another circle, and anytime a radius from the center of a circle hits a chord, always hits at a right angle, and it always splits it in half, so there's another 3 over here, although we're not going to use it. So if we figure out what h is, well, by Pythagoras, h squared plus 3 squared must be equal to 5 squared. This is going to be a 3, 4, 5 triangle. You can, of course, expand this out and rearrange it if you're not familiar with your Pythagorean triples, but I would suggest, again, if you're trying the last few questions on the Euclid, you make yourself familiar with some of the basic Pythagorean triples. 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25. These are some good ones to know. So h is going to be 4. And so the top of the sphere is 4 plus 5, 9 above the plane. They don't give us meters or anything, so it's just 9 units. So we have a height of 9 above the plane, and I think that's all we were asked for. How high above the plane of the triangle is the top of the sphere? We answered that marvelously. And that does it for B. We drew some pictures, we got a sense of the 3D situation, we found some circles and some triangles, and those are 2D objects. We're more familiar with manipulating them. And we were able to use 2 pictures, looking down from above and looking at the side, and some of our knowledge of circle geometry. We got the radius of the in-circle, and we translated that into how high the center was above the plane of the triangle, and then we added on 5, because it was the radius of the sphere, to get to the very top of the sphere. Okay? So, good B part. I really liked the A part as well. I'm sure there are a bunch of different ways to use those similar triangles in part A. If you had a different way, I'd love to hear it. But that does it for question number 9 on the 2002 Euclid. We're going to take a look at question number 10, which is the very last question on the contest, in the next video. So if you haven't tried it, stop it right now and give question number 10 a try. And I'll see you for that question in the next video. So long.